Welcome everyone. So this is our 30-second live stream geometry. We have 6 people here with us already. And today we're going to go over the Taiwan IMO training. So I took problems, I think from the years 2020 and 2019. But there's also problems from the years 2018, 2017. So maybe I could do those on a later session. But the problems looked really elegant. So I was pretty happy to see them, and I'll share my screen right now. All right, here we go. Whoops, sorry. So here's the first of the problems. All right, so we have a scalene triangle ABC with orthocenter H and circumcircle omega. So I'm going to draw the circumcircle and the orthocenter, but I want to see the altitude, so I don't want to just use the orthocenter tool. Let me make it an acute triangle. There we go. So here's the orthocenter H. First, actually, I'll draw the feet of the altitudes. Oh no, they already used D later, so I can't call it D. Okay, I'll just call this H for now, and then I'll relabel the other points later. So this is H, and I draw the 3 tangents to the circle of A, B, and C. I'm going to hide some stuff later, but for now, I'm just going to draw the 3 tangents. My tangents here, here, and here. And the tangents at B and C meet at point B. So we have like a symmedian configuration. So AB is a symmedian. Let's see if I can make it look nice. All right, so this is point B. Now I'm going to label the 3 feet of the altitudes. I just had to say D for that point. Let me hide some stuff. I'm just going to draw these segments. And the feet of the altitudes from H to this, okay, so we draw the altitude from H to this tangent line. And then we also draw the foot of the altitude to AD. So we know AD is a symmedian by the symmedian theorem. So, and we have like a cyclic quadrilateral through all these points. So, so this should be P, and this should be Q. And the problem says that show that PQ bisects BC. This actually already looks a little bit familiar because, I don't know, I feel like I've seen problems like this before, but we know that all these points lie on a circle with diameter AH because those are all right angles. So yeah, I'm just trying to think what I should hide and what I should show here. You know what, I'll just draw this intersection point right here. And I'll just hide. I think this will look good. All right. So let me draw that cyclic quadrilateral because that's probably useful. Circle with diameter AH. So we want to show that PQ bisects BC. Okay, yeah. So A, B, C, and D are in harmonic conjugation. So that's how you say that. Or you could just say their cross ratio is 1. But yeah, but I think what you really mean, so yeah, this tangent line, and then, so yeah, those 4 lines are in harmonic conjugation. So yeah, PQ, G, and F are in harmonic conjugation, those 4 sort of rays. And so then, yeah, and if we label the midpoint of BC, yeah, so that's one way to write it. Yeah, so So I'm just going to label this point just for the heck of it. But okay, so we want to somehow, I want to try to project onto BC. So oh, this problem is too trivial. Okay, I think some of the later problems are going to be harder, but this one looks very easy. Okay, so we solved this right away. Yeah. All right, so I'm going to type up the solution. But yeah, I think they should get harder. They just, but I guess it's good to start off with an easy one. So, so we have the tangents at B at B and C and AK concur, and that means that ABCK is a harmonic quadrilateral. So and yeah, if the problems are too easy, Urijan showed me another problem that he suggested I go over if I finish all of them. So I can take a look at that. So AB plus ABKC is harmonic. So that means the cross ratio AK BC is equal to -1. So and then what I could do is I could project those 4 points. So concur at B. So I could project through A onto the circle with diameter AH. So actually, let me first prove that that's cyclic, just to write it out for the YouTube audience. So we have angle APH equals angle AGH equals angle AQH equals angle AFH, and that implies that AGQ or AGHQF is cyclic with diameter H. Whoops. Let me try this instead. See if that fixes the, oh, whoops. There we go. Diameter. And so we could project, so projecting through A, onto the circle that we just showed was cyclic. So AGHQF. Now we have that. Then we have AQGF is harmonic. So AQGF is harmonic, and once we know that, we can project, or I should say PQGF, right? Because when we project A through A, it's the tangent line to A. So then we can project that onto BC. So projecting actually, hold on a sec. Did we even need to do that first projection? Wait, I think we want to project through. Wait, so we know PQGF is harmonic. So then, yeah, I'm actually not sure. Wait, so is it that once we know PQGF is harmonic, do we project through P? Do we project Actually, now I'm not sure it's that obvious, is it? You guys see what I mean? I thought it was obvious, but now actually I'm not so sure. So Hakan, did you think once we know PQGF is harmonic, JG and JF are tangents. Oh yeah, we have to use that tangent theorem. Okay, so yeah, then that solves it. So by a well-known theorem, JG and JF are tangent to the circle with diameter h. So I'll say that by a well-known theorem or angle chase, JG and JF are tangent to the circle with diameter AH. So PGQF is harmonic. And then, so since PGQF is harmonic, PQ passes through J. So all right, so I'm going to move to the next problem. That was a fast one. Does that make sense to everyone? Or angle chase, or Ira John says an angle chase also works. Interesting. All right, so I will move on to the next one. This is kind of interesting. So we have a triangle ABC with in-center I. We draw the in-circle. And the in-center. There we go. D and E are on rays BA and CA. Let me see if I draw the ray tool. So, so BD is equal to CA. Somebody use the compass. So, and CE is equal to BA. Okay. So this is D, and this is E. We want to show that DE passes through the orthocenter of triangle BIC. Let me
draw E is on the circle.
I'm sorry, what did you say?
You draw wrongly.
Oh, I didn't draw it right.
In circle.
Let I be the in-center. D and E are on rays BA and CA.
He is not on ray right now. He's on circle.
He's on the circle. Wow, you have good eyes. That's kind of hard to tell on that. Yeah. Okay, so let me do it like that. And I will hide all the extra stuff. Let me hide this line. Okay. So I want to show that DE passes through the orthocenter of BIC. So yeah, let me draw the orthocenter. This is interesting. I'll make it look a little better, but okay, so this point right here would be the orthocenter. I could call it H, I guess. And we want to show that DE passes through H. BB equals AC and CE is equal to AB. It's kind of an interesting configuration. So another way to say it is that I is the orthocenter of BHC. That's equivalent. All right. Let me see if I can make this diagram look nice. Yeah, I don't want to make it look like E lies on the circle. So yeah, I guess that's probably good enough. Maybe Menelaus or something. Maybe Desargues. So whenever I see equal segments, I usually either think congruent triangles, or sometimes there's stuff with like spiral similarities that you can do when you have equal segments like this. So yeah, what if I drew the circumcircle? I wonder if ABCH is cyclic. Let's see. No, ABCH isn't cyclic. But sometimes there's like things you can do. So AB is equal to CE. I wonder if I take the midpoint of arc BC. Let's see. So I'm going to draw the midpoint of arc BC. And then is FAB congruent to FEC? I don't know that this will help, but it's just kind of a guess. So I think FAB is congruent to FEC. I've just seen this idea before. Because we have a side that's the same. We have an equal angle, and FB is equal to FC. So yeah, FAB and FEC are congruent. I guess I don't know if that's going to help, but I'm just kind of making a guess. So FAB is congruent to FEC, and actually, let me just keep that in my brain.
DE and AF perpendicular.
DE and AF. Let's see. Are they perpendicular?
Yeah, they are probably.
Yeah, they are. Interesting. So yeah, that's probably true by symmetry, because I think do we have other congruent triangles? So FDB is congruent.
It's the X angle bisector.
Okay. But I think FDB is congruent to FAC, right? Yeah. Oh, and it looks like it passes through E. Huh. So yeah, we have a lot of just, so FDB is congruent to FAC. So yeah, I guess F is the circumcenter of ADE. And I feel like we're really close now. Yeah, if F is the circumcenter of ADE, we have all these different congruent triangles. It almost feels like the problem has to be solved any second. But yeah, let's see. Yeah, because FEC is congruent to FAB. So FE is equal to both FA and FB. So F is the circumcenter of ADE. And yeah, so these have to be perpendicular. So yeah, we know DE is perpendicular to AF. If we could show HE is perpendicular to AF or something like that, we would be good. So I think that means this line passes through the center of the circle BHC. Yeah, it feels like we're very close, right? Checking who's on. Let's see. But we haven't used that I as like the in-center, right? So I feel like that we want to use eventually. So yeah, maybe like the in-center, X-center lemma, because yeah, let's draw the midpoint of arc BC also. So we could call this point M. And maybe it's worth just drawing the center of the circle ABC. So I could call that O. And why did I do that? I wonder if these circles are the same size. Actually, I don't think they are. No. But yeah, what was I gonna say? Oh yeah, let's. Okay, this is getting a little confusing, but I'll draw the circumcircle BHC. Basically, we're saying BH passes through the center of that circle. So I'm gonna erase some stuff. Don't worry. But yeah, that would mean that passes through this point G. Yeah, I'm just thinking through. So yeah, really we want to show DE passes through point G, which is the center of the circle BHC. So AI passes through M, and then if we draw HI, that's going to be perpendicular to BC. I'll draw this point. Yeah, we have to use that I as the in-center somehow.
Are HAB and HEC similar?
HAB and HEC?
No, not okay.
I don't think so. Yeah, that's a skinnier triangle, HAB. But FAB and FEC are congruent. And yeah, F is the circumcenter. Does it pass through? Wait, hold on a sec. Yeah, no, it doesn't pass through O. It just looked like it in that diagram. Yeah, it's hard to draw everything good. So yeah, DE is perpendicular to AF. If we could show DE passes through G, then that would solve the problem. Because we know HG is perpendicular to, actually, is that, wait a sec, so HG, I'm just assuming we could show HG is perpendicular to AF. But yeah, let me check. And there's actually a right angle. Yeah. Let's see. Yeah, we have to use that this is the incenter, right? So A, I, and M are collinear, and M is the circumcenter of BIC. Maybe that'll be enough. I'm not positive. So M is the circumcenter of BIC, and H is the orthocenter. Does that help tell us anything? So basically, like in triangle BIC, IH and IM would be isogonal. I don't know if that, how much that helps. Or I think IJ and IM are isogonal, right? So angle BIJ, I think, is equal to angle CIM. Yeah. So I think triangle BIJ is congruent, is similar to triangle ICM, right? Because those are both similar triangles with an equal angle. So a spiral similarity takes IBJ to IMC. That seems like it's probably useful, right? I don't know, but I'm just making guesses here. So IBJ is similar to IMC. And also IBM is similar to ICJ.
I think we should find similar triangles. DHA is similar to something and AHE is similar to something.
Okay, so DHA, trying to think. Yeah, so if we had those similar triangles, maybe we could use ratios to get another pair of similar triangles. Let's see. Let ABXC be a parallelogram. Okay. Let's see. So if this was like point X, then XC equals XE and XB equals XD. I feel like I've seen things like this a lot. I'll add that point X just for the heck of it. Oops. First, let me draw. Oh, it looks like that point is on this circle. Well, yeah, of course it's on that circle. So I'll call it X. And all right. So DE is perpendicular to AF. Can we show that I think we can show HG is perpendicular to AF, but how do we know? Can we show that G lies on HE? I feel like we just want to show G lies on HE. That doesn't feel like it should be that hard. Although I don't know for sure. Is triangle, yeah, so we have AB equals CE. CEF is congruent to FAB. I wonder if we want to show HG. So we know HG meets the circle at a point that makes a parallelogram with I, B, and C. So if HG meets this circle, it's kind of hard to tell which circle, but if we draw this point, I think it's this point, yeah, then IBKC is a parallelogram. Do we know D, E, and X are collinear? I think we could prove it not too hard. No, I think we could show H, E, and X are collinear. D, E, and X, I feel like we're very close here. So IBKC, yeah, it's hard to know what we know and what we don't know about what's collinear. So I'm going to hide that. But let HG, yeah, we don't even really know that HG and we don't know that HG and E are collinear, but let HG meet the circle at K. Is AD equal to AE? Whoops, I accidentally hit A. AD and AE, I'm not sure, but it looks like it from here. Huh, yeah. Oh, no, that is true because triangles, I think we had congruent triangles somewhere, right? So, what was it? But yeah, it looks like AD is equal to AE. Well, it has to be because BD is equal to AC, and AB is equal to CD. So if you just subtract the two, it has to be true. Oh, so then it's just an angle chase, I think, right? Because I'm not positive actually, but we could calculate all these angles. So if we can show that DE passes through point K and HG, so HG, we define it to meet at point K, and then IBKC is a parallelogram. So if we could show that DE also passes through point K, that would solve the problem. So IBKC is a parallelogram, and we want to show that DE passes through K. That seems like it should be doable. Well, yeah, we'd also have to show HG is perpendicular to AF. I think we'll be able to do that though. Let's see. So yeah, is there a good way to show DE passes through point K? And we know JK is parallel to BC. So a lot of stuff here. Yeah, it feels like there's just so much information that we have to be able to solve it eventually. So we have AE is equal to AD. If that's true, so yeah, JK is parallel to BC. It looks like these three concur. Is that obvious? No, they don't concur. It just looks like it from that diagram. And it looks like they also pass through point X. Just, I can't prove that it passes through, but I think it probably wouldn't be that hard of a proof. Well, wait, actually, yeah, we could show that HG, I think we could show not too hard. Yeah, I'm trying to show that DE passes through K. E lies on the angle bisector of BXC. Interesting. Whoops. Sorry. My GeoGebra is acting weird. BXC. And is it obvious that E lies on that angle bisector? Oh, because ADE is isosceles and CEX is isosceles. So yeah, from there we could show E lies on that angle bisector. And then can we show H and D lie on the angle bisector? Let's see. So D lies on it. So yeah, D and E both lie on that angle bisector. And can we show G lies on it? I wonder if GV, let me try something. Yeah, I think GBXC is cyclic. And that's probably just an angle chase because, oh, actually, I'm not 100% sure. Let me check it. Yeah, GBXC I think is cyclic. Let's think about that because GBC is twice BAC. Now I don't see why that's true because G is the center of a different circle. So yeah, I think an angle chase can show that GBCX is cyclic. And since GD equals GC, then G lies on the angle bisector of BXC. So H, E, and G all lie on the angle bisector. I'm sorry, D, E, and G lie on the angle bisector. And as far as H, let's see. So GBCX is cyclic. And so I think we can show H is the X center of XBC. All right. And let me think about that. Because K would be the in-center and yeah, how do we show H as the X center? Because we don't know HK is a diameter yet. Like, can we show AIC is similar to XCH? Since HB is perpendicular to XB. I think you mean HB is perpendicular to KB, but how do we know that? Because we don't know yet that H, G, and K are collinear. Well, oh, we do. Yeah, H, G, and K are collinear. Okay, so yeah, that solves it. So yeah, since HB is perpendicular to CI, then HB is perpendicular to KB. Okay, so we've solved it. So I'm going to start writing it up. So yeah, I don't think I need everything in this figure. I'm going to, I'm not even sure what I should or shouldn't keep. I don't think I need this circle right here. I don't even think I need point M. Or point F. Well, no, I think I want to keep F. But actually, maybe I don't even need it. If I just create point X, like Irijan said, and I show that XBGC is cyclic, well, I want point F to show that, but maybe I don't even need it. Yeah, I don't even think I need point F. I think there was probably a solution using point F, but I think Irijan's idea works. So I don't think I need point F. All right, so first I'm going to show that BGCX is cyclic. I don't think I need point J. Okay, I think this should be good. Okay, so let G be the circumcenter of, in fact, do I really even need, I could let K, I could just define K to be the antipode. Okay, so let me just think how I did this. So ADE is isosceles and CEX is isosceles. Oh, but I don't know that DH and E are collinear. So, but I can use an angle chase to show that they're similar. So, yeah. So DE and X are collinear. And then, so X lies on the angle bisector BXC. For that reason. So I'm sorry, so yeah, D and E lie on the angle bisector BXC, and H, we showed H as the X center because if we let HG, so yeah, how do we show K as the in-center of triangle B? Because yeah, then it would just be the in-center X-center lemma, I think, right? So okay, yeah. So I'm just going to start writing up stuff. So let X be the point such that ABXC is a parallelogram. Okay, so first we have AB equals CE equals CX, or I'll just write it CE equals AB equals CX. So triangle CEX is isosceles. And then we also have AD is equal to AE because we have AD is equal to BD minus AB, which is equal to BD is equal to AC. So that's AC minus CE, which is equal to AE. So that means AD is isosceles. So yeah, this is a different solution that doesn't use that point F. And angle ECX is equal to angle DAE. So that means that DE and X are collinear. So A, B, and X are collinear. Okay. And now we want to show that, and not only that, XE, the ray XED bisects angle BXC because we have angle, we'll say it like this, angle BXC equals angle XEC is equal to angle EXB. So that implies the ray XEB bisects angle BXC. Okay. Sorry about that. XED. And then we want to show H also lies on the angle bisector. So we want to show H is the X center of BXC. And so think about that. So BGCX is cyclic. I think you need that for the solution. And then you could use the in-center X-center lemma. I don't know if there's an easier way. Well, if we can show so yeah, that would do it. So first I'm going to show BGCX is cyclic. I'm not sure if this is the easiest way to go about this. So yeah, let G be the circumcenter of HBC. Okay, so I'll write that at the top. Let G be the circumcenter of triangle HBC. And K be the antipode of H. Okay. And so BGCX is cyclic. So I can show that by an angle chase. So XG, so since BG equals GC, XG is an angle bisector. So, but we still have to show H and K lie on it. But we could show H as the X center. I guess we could, if we show K as the in center, then by the in center X center lemma, H is the X center. And K is the in center. That's a really easy angle chase. So I think I'm just gonna do it that way. So so hold on just a second. So we have angle BXC is equal to angle BAC, which we can write BAC in terms of, I think BAC, so what is BAC in terms of BIC? So this plus this is B over 2 plus C over 2, which is 90 minus A over 2. So BIC is 90 plus A over 2. So if BIC is 90 plus A over 2, BIC is so 2 times BIC minus 90. So I skipped a bunch of steps here, but you can calculate angle BAC as twice times angle BIC minus 90. And that would be, and BIC is 180 minus BHC. And that would be 180 minus twice angle BHC. I think that, well, no, I want to show BHC is 180 minus BXC. So let me see what I did wrong here. But so this should be like BHC over 2. So is this BXC is BAC. Let me write out the algebra. So BAC is 2 times, oh, the 90 should be outside the parentheses, I guess. But would that still, so you're saying it should be like this, right? So twice B. Are you sure though? Because twice BIC would be really big. Would be like, BIC is obtuse. So twice that would be 2 obtuse angles. I think that would be too big. Let me see. So you see what I mean? So minus 90 minus A over 2. 90 plus A over 2. So BIC. Oh, sorry. So yeah, I think it is like this. And then BIC, I think it is 180 minus BHC. So oh no, this is right. I wanted to show BGC axis thickness. So this is 180 minus, yeah, that was right. So that's 180 minus BGC. And so BGC axis thickness. And then, my bad. And then BG equals CG. That means that G lies on the bisector of angle BXC. And that implies G lies on HE, or G lies on DE. Because we know those both lie on the angle bisector. And then we want to show, and then K we could show as the incenter. So yeah, and then HE and K, or HG and K would have to be collinear. So yeah, so I'm going to show K is the incenter, and that's really easy, I think. Or I could show H as the excenter, like you said, but I think showing that might be a little more angle chasing. I'm not sure. So
what is point H?
H is the orthocenter of triangle BIC. So maybe I can write it at the top. Let H be the orthocenter of triangle BIC. So yeah, do I need point K? So I could show K as the incenter, and then I can use the incenter X center lemma to show that H also lies on it. Or I could
yeah, you could angle chase. E the angle EGC is equal to XBC and equal to ACB. So now we have to prove that yeah, and HGC is equal to 180 minus HBC. That is yeah, of course, after angle chasing, we prove that H and G and E is collinear.
Okay, I'm actually gonna do something. So we have so BX is parallel to AC. So I want to show BK bisects angle CBX. So but angle KBX is equal to angle ICA because they're both parallel. And yeah, I see a couple ways to do it. Sorry, let me think about it for one more second. So okay, we could try to show H as the X center. I think we're really close to being done. So we know actually that HI I guess we need to show that H is the X center, right? We need to show either that H is the X center or K is the N center of triangle BXC. So so yeah, I'm trying to think about how to do the angle chase to show that K is the N center. So angle KBC or angle KBX would be equal to angle ICA. So we want to show angle ICA. We want to show angle ICA is equal to angle KHC, which is the same as angle KBC. So we want to show KBC. Okay, I think I got this. So we have angle KBX is equal to angle ICA. And that's equal to angle ICB, which is equal to angle KBC. Yeah, that's it. So and then similarly, we have angle KCX is equal to angle KCB. So K is the incenter of triangle BCX. And then by the incenter X center lemma. So that means that means that K lies on ray X E G H. And then X, K, G, and H are collinear, implies H lies on B. I think this is good. So yeah, KBX, let's see what everyone wrote in the chat. Yeah, I think it would probably work what Irajan said, defining K to be the incenter. But I think this works for now. I am going to move on. So KBX is equal to ICA because we have, because KB is parallel to IC and AC is parallel to KX. So I'll just add that in for the people on YouTube. So so KB is parallel to IC, and BX is parallel to AC. All right. Thanks everyone for the help on that. So yeah, we ended up doing a different solution, not using point X. So that's kind of interesting. All right, so here's the next problem. So I is the incenter of ABC. Yeah, I feel like I just got caught up a little bit in the calculations on the last one. But sometimes that happens. I is the center of C. BI, okay, so we draw the phi of the angle bisectors. And then we draw the circumcircle. So is there a D in the problem? There's not. So E, let me try to make this point look better. This will be point F. Let me draw like a tall triangle. Then E and F won't be so close to the circle. Make it tall. Maybe something like that. All right, and then we draw the intersection. So I think this is the, well, no, this isn't the Sharkey double point. I think Rodrigo on the Discord chat sent me a problem like this, where you have the intersection of these two circles, AEF and ABC. So we're calling it R. And M is the midpoint of BC. And P and Q are the intersections of EF with AI and MI. So we draw AI and then we draw MI. Let me make this look a little better. Maybe something like that. So this is P and this is Q. And we want to show, yeah, let me make them a little farther apart. Let me think how to do that. I'll make the diagram a little bigger. So that's P, this is Q. We want to show APQR is cyclic. Yeah, let me make P and Q farther apart. I don't like that they're so close together. I think I'd have to draw like a flatter circle then. Yeah, I'll just leave it something like this. Let me hide some extra lines. All right, so BIE, CIF, like this. There we go. And let me delete this point D way out here. See if Prabhuda, I see you joined. Thanks. So, yeah, this looks kind of hard, I guess. I agree. Yeah, there's not that many problems that have like the feet of the angle bisectors like this. So, 1 second, guys. I'll be right back. All right, thanks for waiting. Let's see who jumped on. Can I label the intersection of AR and EF? Yes. So I'll call that D. This seriously looks projective. Yes, I agree. So I wonder if I should draw the intersection of EF and BC. Because that would give me like a harmonic. It looks very projective. We want to show DF times DE equals DQ times DP. Yes. Taking draw a bundle through I, draw a line parallel through I parallel through I to BC, or through I to EF. I guess BC probably, right? Yeah. Let's see what that does. So but let me just, instead of drawing another line, let me unhide the line that already existed. There we go. So I'll let G be that point. Let's see what that does. So if we project through I onto project BMC through I onto EF, we would get EFQG is harmonic. I'm not that sure. And then maybe we could project onto the circle itself. I don't know. So EFQG is harmonic.
We can use power ratio lemma.
Oh, really? Yeah, because we want to show P and Q lie on the same circle passing through A and R. So yeah, maybe power ratio lemma helps. I think that actually might be the best idea. Yeah, actually, when I first saw this problem, I thought about power ratio lemma, but then I just forgot about it until you brought it up right now. So thanks for bringing it up. let's see. So what would be the powers of P and Q with respect to the big circle? So P lies on AI. So if we drew this midpoint, we could find the power of P with respect to the big circle. For Q, maybe we could use like the IM lemma or something. I'm not sure. Yeah, I'm not sure how we would find the power of Q with respect to the big circle. That's what might make it hard. I wonder, this would be really surprising, but I wonder if Q lies on AH. No, close, but not quite. I like the idea though. Maybe there's something special about.
It is through the midpoint of AH. Maybe we can use this.
Use the IM lemma. So yeah. So yeah, MQ passes through the midpoint of AH. Not sure how much that helps, but yeah, I think that's the main problem with using the power ratio lemma, is that it's hard to get the power of Q with respect to the big circle. Doesn't mean it's impossible. There might be a way, but maybe we could try this. Yeah, I'm not sure how much that helps. No, just keep the figure like it was before. Is DB tangent to the circle, to the circumcircle of ABC? Looks like it. Oh no, that was an illusion. But can we use radical axis theorem somehow? Because F and E aren't on the in circle, so that makes it a little tricky. Is there some? This would be really unlikely, but I wonder if H is the antipode of A. Let's check it. I don't think so. Nope. So yeah, MI bisects AH. And if we draw the topmost point of the in circle, MI is parallel to that segment. So yeah, maybe it's worth drawing the, I'm going to draw the topmost point of the inner circle. So IM is parallel to AH. And M is the midpoint of HJ. I wonder, let me see if there's another circle that passes through P and Q. Then maybe we could use the radical axis theorem. Doesn't look like it. Still, I'm not willing to give up on it just yet. The circumcircle PQI. Or yeah, maybe there's another, maybe we could show a different circle as cyclic with A and R by the power ratio lemma. So I don't know exactly what that circle would be, but I'm just trying, checking out different ideas. E, P, Q, and E. If we knew those were harmonic, how would that solve it? Oh, it's all right. But I think there is something. So, okay, we want to show, so like a concept, we want to show df times dE is dq times dP. The only thing is, yeah, if we had like midpoints, but we don't. So let me check. ARH.
Michael.
Mm-hmm.
If we could just let AP cut the circumcircle AEF at a point. Let's call it K.
I'm sorry. So ADF, is that what you said?
AP.
Oh,
intersects the circumcircle AEF at K.
All right.
Yeah. So if we prove that RQK is collinear, so the problem is so.
Oh, really?
Yes.
RQK is collinear by oh, I was going to say the Sharkey-Devil theorem, but no, it's not actually. It's something similar to it. Okay. So and how did you get
proof? Yeah. So we need to prove that RQ is the bisector of FRE.
FRE?
Yeah. RQ.
Okay. So yeah, once you show that
QF on QE is equal to RF on RE.
Okay.
Yeah, but RF on RE is equal to FB on EC.
Because they're similar triangles, RFB and REC, right?
Yeah. So we need to prove that QF on QE is equal to FB on EC.
Okay, so I see how to do
Okay.
that.
Yeah. Okay. You know the Sin's theorem. Yeah. In the triangle FIE, so we have QF on QF on IF is equal to sin F EQ on sin FQI.
Okay.
Yeah, it's similar to QE. So we have FQ on QF on QE is equal to sin FEQ times FI on sin QE QIE times IE.
Okay.
Yeah, yeah, and we change the angle. FIQ is the MIC.
FIQ is MIC
Yeah, MIC because
of the
I
collinear.
am
Yeah, FIQ
yeah
is MIC.
yeah, and QIE is BIM.
Okay.
Yeah,
So,
and we use that again. Just let me tap it for you. Okay.
okay, thanks.
Okay.
Let me check if I'm just gonna look at Iridan's question. Is AQ a semedian? Let's see. So angle BAQ is 17.6 and angle MAC, it is. So AQ somehow is a semedian. Maybe that's like a well-known theorem. Interesting. Barry Bashworks. Yeah, Barry Bashworks to show semedian. I wonder. It seems like there has to be. Yeah, to show because. I wonder if like we drew the parallel through Q to BC, there would be a way to do it. But yeah, I try to avoid Barry Bash if possible. Yeah, it's probably a good idea during a competition, I'm sure. Let's see. So yeah, adding the point K, it kind of reminds me, let me draw the perpendicular bisector of AI. The perpendicular bisector of AI. Oh, it looks like G is on the perpendicular bisector of AI. Yeah, so this line passes through. This reminds me a lot of a problem that Rodrigo sent. So it passes through both the midpoints of AB and AC, and it looks like G also lies on that. Interesting. So that looks like it's probably an angle chase. So we want to show that GI is equal to GA. I wonder if GA is also tangent to the circumcircle. Yeah, this is looking a lot like a problem that I solved on the Discord channel. Oh no, but I don't think it is tangent to the big circle. Or is it? Now I'm starting to think it is. Yeah, I think it's tangent to the big circle. Okay, so I think there might actually be another way to solve it. Yeah, Dat Fung, feel free to keep typing up the idea you had. And yeah, that's the solution I'll probably end up doing. But I think G, yeah, I think GA is tangent to the circle, and GAI is isosceles. So maybe that would help solve it. Because yeah, then we want to show AQ times AP is equal to, or GQ times GP is equal to GA squared. And GA squared is GL times GN. I feel like this would probably also, there's probably also a way to solve it like this. So that would mean LQPN is, maybe I went wrong somewhere. Oh no.
Yeah, I have already tap it on the chat. You can look at it.
Yeah. So okay, so you prove that QF over QE is BF over CE. So I agree with that. I agree that QF over QE is BF over CE. But then you're also saying it's BF over CE is IC over IB. Okay, so but so I agree with that. And then how do we use that to show that ARQP is cyclic or APQR is cyclic?
Oh, if KQR is collinear, so KP times KR is equal to KE square and
Okay.
equal to KQ times KR. So that is a cyclic.
Okay, so yeah, if K is the midpoint, then basically for any two rays, actually it's cyclic, right?
Yeah.
Like even if I had and you can probably use inversion to prove this, I'm sure, but like even if I had like these 2 points, it would be cyclic, right? SOP.
Yes.
All right. I think that is probably the best idea conceptually. So yeah, we want to show R, Q, and K are collinear, and then that solves it. And the thing that you showed, does that help with showing that R, Q, and K are collinear?
We proved that RQ is angle bisector from ratios, so it passes through K.
Okay. So and then that solves it. Very nice. So yeah, it'll be interesting to see after the session if there's a solution with point G, but for now, that is a very nice solution. So I'm gonna start writing it up. All right. Did we need point? Yeah, we didn't need point D for this proof. Okay. So yeah, that'll also be interesting to show how AQ is a submedium. All right, so start typing it up. Let's make some more room for the text. So yeah, we don't need H prime. We don't need AJ for that proof. Or whoops, did I delete? Yeah, we don't need that. I think, so is RFB similar to REC? I think there might be a way to simplify some of the steps in Feng's proof. So yeah, we want to show, so yeah, RF over RE is equal to BF over CE. I think that's just true by similar triangles, right? Because so angle RBF is equal to angle RCE. So that
we need QF on QE is equal to RF on RE.
Okay, so yeah, ultimately you need the QF on QE. So so that's where you started using the law of sines. But maybe there's like another way, because let's see, what if I so yeah, let me just think for a couple seconds, and if not, I could do it. So yeah, BF over FQ is CE over EP. And Yeah, I wonder if it's just similar triangles because let's see. So we have a triangle right here. What if I, for example, yeah, I'm just thinking if there's a way to avoid the law of sines. So FQ. So yeah, like if we knew AQ is a symmedian, then FQ over QE. I'm just thinking about this. So yeah, you used sines. QF over QE. Let's see. So yeah, I see what you did. So you said it's IC over IB. Let me check something. I wonder if these angles add up to 180. So this is 93. This is no. Q equals sine CIM over BIM. So yeah, maybe we could just use like projective geometry. So basically, okay, okay, you're saying, so if we have QF over QE, if we project through I, but you want IC over IB. Yeah, so I don't think it's that easy. But for example, if we oops. Yeah, I wish this thing would disappear. It makes it like tricky. But basically, like let's say we project FQE through I onto line BC. So we have FQE infinity. We project it onto this. Then we would get BC, M, and D. And M is the midpoint. So BM over MC is 1. So that would be DD over DC. And if we could show that angle DID is equal to angle ICB, I think that would do it, right? And whoops, maybe not. So what did I want to show? I want to show, yeah, are these triangles similar? Let's see. No. Q infinity. So IB over IC. So wait, so you're saying IC over IB, you're saying is QF over QE. Do you kind of see what I'm saying here? So QF over QE, that's the cross ratio EFQ infinity. And then if I project through I onto BC, then I would get CBM MD. And I want to show that is the same as IC over IB. Maybe that means that these are isogonal. Let's see, 28.6. No. Or maybe that means that this is 28.6. I don't know.
Michael, if you let AI cut BC at L.
Mm-hmm.
Yeah. Yes. So we have this. Okay. Is J is okay.
Okay. All right. So then I could project FPQE.
Yeah. Just project the ion. So we will have that MB on MC times GB on GC is equal to yeah.
Yeah, that works. I like it.
Yeah.
So all right. So first I'm going to start out. So by a spiral similarity at R, by a spiral similarity, RFB is similar to REC. So we have RFB is similar to triangle REC. And so so we'll say let AI meet the circle AEF at K. All right. And whoops, sorry. So RF over RE is equal to FB over EC. Actually, I wonder. So, okay, and then we could BF over CE, and then we could project through I. So hold on just a sec. BF over BC. Okay, so we want to show that this is actually QF over QE. So if projecting through I onto BC, so we have EF QP is equal to BC MD. So now I'll write this out as fractions. EQ over QF times PF over PE is equal to BM over MC times CD over DB. And, okay. So,
Yeah. But BN is equal to BC.
oh, I'm sorry. I think your volume went up for just a sec. So we have EQ over QF. So PF over PE is equal to AF over AE, right?
Yeah.
And BM over MC is 1, and CD over DB is AB over AC. So I think we did that, right? So
Yeah. Because PE is the bisector of ABC, so EA over EC is equal to AB over BC. And
so I'll write it like this. So we have EQ over QF is equal to so it would be AE over AC times AB over AF. And then we could use angle bisector theorem. So that's AB over AC times AB over AF. I think AE over AC is A. Yeah. Let me see what I did.
we have to put BC into it. BC. Yeah.
Yeah. So this should really AE over AC is really AB over AB plus AC, I think, right? So this is.
Oh, okay.
Yeah, and then AB over AF is AB plus AC over AC, I think. Let me check that this right, but I think it oh, whoops. What happened here? So let me add in one more line. So that's 8 AE over AC. There we go.
Oh no, the last one it is not correct.
AB over AF. So it should be AB plus AC.
No. We shouldn't do that. Michael.
Okay.
Okay. We still let AE over AF times AB over AC.
Okay.
Yeah, and AB over AC is equal to AB over BC times BC over AC.
Okay. So you're saying do it kind of like this. So it's AE over AF times AB over AC.
Yes.
And then that so you're adding another fraction. So AE over AF times AB over BC.
Yes. Yeah, that's correct.
Times BC over AC.
Yeah.
Okay. And then we use the angle bisector theorem. So AB over BC is AE. I like this.
Yeah.
So that's AE over AF times AE over EC. And then this is EC over AE.
Michael, I found that you did it wrong.
Okay.
DC over DB have to be AC over AB.
AC
The over up. Yeah.
Yes.
That's one. Yes.
Okay, so this could be AC over AB.
Yeah.
Yes, you're right. So, all right. So this should be AC over AB. And then this is AC over AB.
Yes.
And then AB. And then AC over BC is AF over FB.
Yes. No, that's correct. AF
Right.
over BF. Yes.
Yes. And whoops, sorry. And BC over AB is CE over AE.
Yeah.
And then we have stuff cancel. So this is CE over BF. All right. And so, so EQ over QF is CE over BF. And so, so then we have RE. Combining it, we have RF over RE is FB over EC, which is by this is QF over QE. So I'll just make some room here. So, whoops, sorry. So combining the above, we have RF over RE is equal to QF over QF, or wait, RF over RE is QF over QE. Imply, and that means that RQ bisects angle FRE, or yeah, FRE. So that means RQ and K are collinear. And then once we know that, then that basically solves it. One way is inversion, but inversion or similar triangles. Yeah, should I write it all out now? Let me think. Just how I want to write it out. So I'll just say by an angle chase. KQF is similar to KFR. So sorry, there's a car honking in the background if you guys can hear it. You guys hear the car? Oh, it just stopped. So KQF is similar to KFR. And KPQ is similar to KAR. And that means that KQ times KR is KF squared is KP times KA. And that means that APQ are cyclic. Very nice. This is a great solution. Thanks, everyone. So now I will move on to the next problem.
Okay.
I like it. All right. So